That's used to solve and kind of display somewhat complex problems and optimize their efficiency, make them the most profitable or the most powerful or whatever it may be looking for. So let's read and understand the problem. You run a business making and selling pots and jars, among other things. Making a pot takes 2 hours and costs $1 in materials. Making a jar takes half an hour and costs $2 in materials. And each week you have 6 hours to work, and $12 to spend on supplies. I'm going to actually pause here real quick and talk about, I was thinking about why word problems like this are hard for students in general. And I think part of it is because you probably don't have a lot of the life experiences that these problems are dealing with. Like my guess is if you're the typical kid, you've gone to school, you've got a family, you've got a home, maybe some shows you watch, some sports you play, or some hobbies. But you maybe haven't had like a job, or like gone to court, or like robbed a bank, or done any of these important things that we adults do in our lives that sort of give us a context for how to do these problems. So what this requires, if you don't have the experience to draw from, is an imagination. You picture yourself as this pot maker, making these pots and trying to make a living, and you start thinking, well, what do I care about? And you might think that what you care about is selling as many pots and pans as possible. But it turns out what your biggest priority is how to maximize your profits. That's your goal, how to make as much money as possible. So if the profit you earn for a pot is $8 and for the jar is $11, how many pots and how many jars should you make each week in order to maximize your profits? That is our goal. That's what we're going to try and find here. Well, the first thing we're always going to do with these problems is set up variables, x and y. X is going to stand for the number of pots sold. We should say made and sold. How many jars should you make each week? We'll just say made, number of pots to make. Y will stand for number of jars to make. I phrased those slightly differently and that was silly. Now we've got to start making equations. We're going to take the information we have and make equations out of them. Well, what are we constrained by? We know that making a pot takes 2 hours. Making a jar takes half an hour, and altogether we have 6 hours to work. So we're going to spend only 6 hours a week making pots and jars, and I guess we'll spend the rest of our time making other things. Well, now we can have an equation that's all about time. Our time equation, it's 2 hours per pot, half an hour per jar, and we have to spend no more than 6 hours. So 2x plus 0.5y has to be less than or equal to 6. Because we could spend less time on it. We've budgeted 6 hours a week to work on this. The other thing that we're going to deal with is money, materials. It costs $2 to make a jar. It costs, $1 to make a jar. Okay, $1 to make a pot, $2 to make a jar, and altogether we have $12 put together. Sorry, I missed one here. $1 to make a pot, $2 to make a jar, and $12 total. So in terms of our materials, money for materials, we have x plus 2y has to be less than or equal to 12. Those are the two main constraining pieces here. Although there is something else that it's worth mentioning and worth discussing. We know that these can't be negative. We can't have negative dollars. We can't spend negative time. So we technically have these 4 inequalities to work with. And these are the things that are constraining what we're able to do, what constrains our feasible region. Now the last part we have to deal with is the profit. And I will set up this equation now. And we have a profit equation. Now we can think of it this way. We know that it's $8 per pot and $11 per jar. So it's 8x plus 11y. Now students often ask, well, what is this equal to? Like, where's the equation? 8x plus 11y equals what? Well, we don't actually know what our profit is, so we can't have it equal to a number. We could define a third variable, p, if we wanted to. This now has x, y, and p. 8x plus 11y equals profit. Or we can set up a new function with 2 inputs, f of x comma y, f of x and y, equals 8x plus 11. And if this looks totally foreign to you, if you're lost by that, you can skip that. This will be the last thing that we play with. How to find the profit. Before we can do that, we've got to figure what's the best ideal number of jars and pots to make. So now I'm going to start graphing. Now before I'm going to draw an x and y axis. So now I need to later. And forgive me, my pen is being more frustrating than usual right now. And I'm going to graph my lines. I'll start with the yellow line, the time line, as it were. Time is 2x plus 0.5y is less than or equal to 6. I can find the x and y intercepts of this. The x-intercept is always c divided by a, which in this case is 6 divided by 2, so it's 3. The y-intercept is c divided by b, which in this case is 6 divided by 0.5. 6 divided by 0.5 is 12. It's not 0. A lot of people think 6 divided by 0.5 is going to be 3. Not 0, but 3. 6 divided by 0.5 is 12. 6 divided by 2 is 3. 6 divided by 0.5 means how many 0.5s can we fit into 6? We can fit in 12 of them. So this has to go as far as 12 on the y-axis, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 would be here. So I can fit that on there just fine. Now I'll do the money equation. I don't want to actually make the graph until I know what I'm looking at. The x-intercept is 12. The y-intercept is 12 divided by 2, which is 6. Sorry, I got the x-intercept by doing 12 divided by 1. There's a 1 here in front of that x, so 12 divided by 1 is my x-intercept. All these things were covered in an earlier video. If you want to go back and find it, it was Chapter 1, Section 1. So both these graphs have to go out to 12. Let's just make it a little bit prettier. We'll go 0, 1, 2, 4, 6, 8, 10, 12. I'm actually counting by ones. I'm just skipping every other box, so it looks like I'm counting by twos. Let's keep this all the same color. 0, 2, 4, 6, 8, 10, 12. Okay, graph the yellow line. It has an x-intercept at 3 and a y-intercept at 12. And it goes like this. Now let's graph the pink line. It has an x-intercept at 12 and a y-intercept at 6. And then it's going to connect like this. And what's happened now is I've created my 4 inequalities. These two here were already graphed actually because they're just the x and y axis. This means they're in quadrant 1. The x and y are both greater than 0. Then we graphed our yellow line. We have to be underneath this. And we graphed our pink line where we have to be underneath this. And our double shaded region, I get to grab, I'll grab my crayon because my crayon's fun. My double shaded region is this kind of disgusting orangey color. It's actually not a bad orange. This region right here is double shaded. What that means is that every single point inside this shaded region works. And they represent pots that are being produced. So the x-axis, remember we defined it this way. The x-axis stands for number of pots. And the y-axis stands for number of jars. Now, this is a beautiful, beautiful thing because we have all the possibilities right inside this little region. Everything that we could possibly do fits in here. If we tried to pick something to point out here, like that's the point 5, 1. Making 5 pots and 1 jars would take too much time. And here is like the point, I don't know, 6, 9. Making 6 pots and 9 jars takes too much time and costs too much money. But everything inside here works and is possible. So now the question becomes, okay, well, what is the best possible point that's going to maximize our income, maximize our profit? And there's this beautiful, beautiful thing called the corner point theorem that I'm going to write like a 5th grader. There, my handwriting is getting better. First of all, a theorem is a theory that has been proven or that is generally accepted. They're very, very special to math, although not entirely as far as I'm concerned, or as far as I know. They probably have in philosophy also. But the corner point theorem tells us that if you're trying to maximize or minimize something, it will always be done at one of these corner points, at the corner points of your little polygon you drew with your feasible region. So we don't have to check every single possible point. We just have to check these 4 points. And 3 of the points we already know. We have the point 0, 0, it's the bottom left corner. This is the point 0, 6. This is the point 4, 0. And this is the point, I don't know what that one is. We have to find that one, and it's not a clear, obvious point. So I can't just say it looks like it's 2, 5, because I don't know what it is. So what I have to do is find this, and I can do this doing substitution, elimination, or I can use my graphing calculator / Desmos. 5.1. I used my graphing calculator to find it. You can also use Desmos. I've shown how to do this in earlier videos, so if you want to go back and find those, this was in Solving Systems of Equations. Now you might be thinking to yourself right now, hey, can't we not make 1.7 of a pot or 5.1 jars? Actually, we can. We can make 1.7 pots, we just can't sell 1.7 pots. So what we could do is it could be a Friday afternoon, and we're making pots, and time is up. When we've made 0.7 of a pot this week, and we say, okay, I'll come back next week, and on Monday I'll pick up where I left off and finish it. And that way we can be a little bit ahead of the game. So even though we can't sell 1.7 pots, we can make them. And we would like to make as much as we possibly can, and then we'll just kind of imagine that like over weeks and weeks and weeks we've made more and more extra pots out of those 0.7 every week, and that kind of plays into our profit. So it's okay to plug in a decimal here. Even though we can't sell 0.7 a pot, we can make it and we can sell it later. Now we take our 4 corner points and we plug them into our profit equation, and we see which one makes us the most money, and that's the game. So I'm going to take my x values, my y values, and plug them in for f. So like f of 0, 0 means I'm plugging in a 0 for x and a 0 for y, and this obviously makes us $0. Remember I said the corner point theorem can maximize or minimize anything? Well, this is our minimizing. If we wanted to make no money, we would make no objects. Then I'll do f of 0, 6. This is making 0 pots and 6 jars. So that's 8 times 0 plus 11 times 6. That's 0 plus 66. That makes us $66. Next is f of, the next corner point was 3, 0. Nope, 4, 0. That's going to be 8 times 4 plus 11 times 0. And that one makes us $32. And the last one is f of 1.7, 5.1. This means I'm plugging 1.7 in for x and 5.1 in for y. That's all that says. So it's 8 times 1.7 plus 11 times 5.1, and that one I will do in my calculator. This is me finding the point of intersection. If you want to check it real briefly, that was how I found it. 8 times 1.7 plus 11 times 5.1. Didn't use the parentheses, but that's okay. 69.7. This actually makes us $3.70 more than making just jars. We want to make 1.7 pots, and we want to make 5.1 jars. This profits us $69.7. That is linear programming. Take a problem and optimize it. Find the most efficient, most valuable, most productive, best way to use your time, money, resources to solve the problem. It's really a beautiful thing. Let's just recap what happened here. First, we read and understood the problem. We imagined ourselves as pot builders. We defined variables. This is our x and y. You have to do this. Oh my goodness, do this. Then we made equations, and they were actually equations and inequalities. We graphed the equations, although when we actually graphed were just the inequalities. That was making our feasible region. We plugged in corner points to maximize the equation. Oh, sorry, we found corner points first. First, we found corner points. We plugged them into our profit equation to maximize it. We found the point that made us the most money, and then we checked to make sure our answer makes sense, which you, oh my goodness, have to do. Make sure your answer actually makes sense. You'll find that it's very often one of these middle points here that maximizes or minimizes something, but not always. Sometimes we could find out, let's just stop making pots and just make jars. That was a very real possibility here. But what's interesting is you might have thought, wait, don't jars profit us the most? Don't we make 11 from jars? So shouldn't we just make as many jars as we possibly can and then just spend the leftover on more jars? Why are we making pots? Well, even though jars profit us more, pots use fewer resources. They cost less and they take less time. They actually take more time, but they cost substantially less, and that means it's worth making some pots. It turns out, even though jars make us the most money, the best way to maximize all of our profits is not to just make jars, but to make jars and pots in the most efficient way possible. And the best way to find that was, sadly for some of you, through math. So there you go. Hope you enjoyed, and we'll see you next time. Hey, thanks for watching. I hope that was helpful. If you have any questions, leave them in the comments down below. There can be questions about the video you saw here or anything else in math I'm happy to help with. Subscribe if you'd like to watch more videos or see other updates as they come. I'm going to try to run through all of Algebra 2 Trig and then eventually hit more classes like Algebra 1 and Geometry and Pre-Calc and everything else. If you have questions about stuff covered that's not in this video, still let me know. I'm happy to help. And finally, if you're not one of my students taking the class, but you found the video and are watching it, or maybe you're a teacher and are watching it, you can buy the curriculum and buy the worksheets to go through it. That's found at the website listed down below also. So again, thanks for watching. Have a wonderful day.